In this next installment, we are looking at the previous collision, which you remember was two bowling balls hitting each other, and asking ourselves whether it was elastic. If it's elastic, the kinetic energy before will equal the kinetic energy after. So this is fundamentally a question if. Is it true? With momentum, we know it's always true, but we're just trying to see what happens with the kinetic energy. So doing our accounting here, we have the kinetic energy of the 7 plus the kinetic energy of the 4. Does it equal the kinetic energy of the 7 afterward plus the kinetic energy of the 4 afterward? Now, we already see that this is a bouncy collision. So we expect that the answer is yes. The kinetic energy should be the same. So we're now going to ask, are they equal to each other? Well, the formula for the kinetic energy is 1/2 mv squared. Notice we're not asking what is the kinetic energy. We're asking whether the kinetic energies are equal to each other. So if we notice in this equation, every term on both sides has a 1/2. So we can multiply the whole equation by 2, and the 1/2s go away. Now, it may look like we have m's and v's, but the m's and v's are not the same. The mass on this side is 7, with a velocity, if you remember, of 4. So 4 squared. And the other particle, which was 4, had a velocity of -6. And afterward, we had 7, and we said the velocity afterward was -4/7. Plus a mass of 4, and if you remember, the velocity for that particle was 2 in the positive direction. So we have 2 squared. So that gives us 7 times 16 plus 4 times 36. Does that equal 7 times 16/49 plus 4 times 4? So 7 times 16 is about 120, 7 times 16, 70, 112. Yes, 112. And 36 times 4 is 144. And on this side, this 7 and this 7 will cancel. So 16/7 is about 2 2/7. And 4 plus 4 is 16. So we have 256. Does that equal this on the other side? It's like 18 2/7. And the answer is no. The kinetic energy before and after are not equal to each other. Afterward, we can see there is much, much less kinetic energy than there was before. We should never expect to see more kinetic energy afterward. Now, why should this be the case? When two objects interact with each other, the energy that they have can be converted into sound. Most importantly, and most oftentimes, it's thermal energy as a result of friction. When two particles hit each other, there's this vibration inside, and the material and the molecule inside is vibrating, and it warms up the body. The body's interacting with each other. So this is usually the largest source of where that energy goes. So why we did this particular example is that this construct of elastic and inelastic is what we call a false dichotomy. A dichotomy is when we split things into two categories. We say it's an either or. It's one thing or another thing. Well, it turns out this is one of those false dichotomies. All there is are shades of gray. The question isn't whether it's elastic or inelastic. The question is how much energy is lost. That's really the question. Well, if no energy is lost, then the ratio of the kinetic energy afterward to the initial kinetic energy will be equal to 1. If all of that kinetic energy is lost, then that will be 0. And so we can say things are more inelastic, the smaller the number, or we could say they're more elastic, the larger the number. Or we can simply calculate a ratio, and that ratio will give us a nature of the elastic character of the interaction. So we might say an interaction is 0.7% elastic, or 0.7 elastic. That means that 70% of the kinetic energy was present after the interaction. Or we could say 10% or 20% or 30%. The idea of an elastic collision is ideal. It's theoretical. It doesn't really exist. It doesn't really exist. The question is how much energy does remain after the collision. That's what's important. But we should expect, for sure, if two bodies are colliding with each other and bouncing off each other, we would in general expect there to be more kinetic energy left over afterward. And we should also expect that if they stick together, the kinetic energy will be much less. And the reason for that is simple. The kinetic energy formula is dominated by velocities because the velocity term is squared. If two things stick together, then the velocities must really decrease if they stick together. Whereas if they bounce apart, there's a greater chance the velocities will be higher, and kinetic energy is dominated by velocity. And that's this installment.